diet pill plus exercise. And notice here, it does seem like there is some discrepancies, but I don't see that many major discrepancies. In my estimation, they're still towing this line. They're not way out here or way down here. So it looks like approximately normal. So it looks like this is not a violation of normality. This right here, we're not really going to go into the trend lines, but we will look at this, and we see that the diet pill, and that might be the reason why kurtosis is so high, is we have these outliers. These little circles here, these represent outliers. And I think it's participant 15 and participant 19 and participant 2 that has these outliers. And this is a major outlier. I think this asterisk at participant 8. I don't know if it indicates that, and it doesn't. I just double clicked on this, and I don't really see an indication of what that means. But I would guess, I think that's what SPSS indicates as a major outlier, and it's way out here. And it might be the reason why this is highly kurtotic right here. So based on what all we see here, based on these plots here and the normality QQ plots, I would say there's a violation of normality. And so we're going to have to do a different type of post hoc test. That's totally fine. We can move on with violation of normality, but it needs to be indicated right here. So, and I think we did that quite well. So let's go ahead and move on to the looking at how to perform this analysis, the ANOVA analysis. We're going to be filling out this table while we do this. And so I'm going to go back into the data. And what we need to do is go into Analyze, Compare Means, One-Way ANOVA. We've done that. And what we need to do here is, normally we would use the Tukey test, but I think in this case we're going to have to use the Dunnett's test. I'm sorry, what I mean to say is not the Tukey test, but you would use the Games-Howell test. And so if there's an assumption that has been violated, we would look to see where is this Howell test. So you use this one right here. But this is actually for equality of variances not assumed. So I think that's more of a major violation. And if we found that the normality was such a major violation, then I guess we would use the Games-Howell. I'm going to go with this right here. But in normal situations where there's no violations of assumptions, especially the equality of variance, we use the Tukey test. So I'm going to be respectfully cautious and use the Games-Howell test, just to make sure that we're all on the same page that we did violate something, and so we have to do something about it. We can't just settle with the Tukey test. All right, so let's go to the main analysis first. I'm going to not check this off because we don't need this right now. The main analysis, we don't need anything there. In contrast, we don't need to check that off. I don't think we need to script this, but I'll put that in there just in case. And then I'm just going to push OK because we have the dependent variable right here, weight loss, and independent variable right here. I'm going to press OK. And what we should see here, give me a second. Is this table represents this table right here. So not this table, but actually this table. So it conveniently puts the sum of squares down, gives us the degrees of freedom, the mean square, F ratio, and then the significant value. And what we can do is just go ahead and just fill that out to 88.203. And then go into here to 2132.6. 477, and then this one is going to be 2420.97. Just round this up to two significant figures, and this should be 2, and then this should be 78, and then this should be 80 right here. I'm just following this right here. 144.102, and then 27.34. I'm just going to round this to that right there. And then this is going to be 5.27. The p-value is significant. Right, so we'll put this right here for significance, which is 0.007. And then remember to get eta. Eta is not really given here, but that's the effect size. And as we recall, it's going to be 0.01 for small, and then 0.06 for a medium, and then 0.14 for a large effect size. And what we'll do is take the between divided by the total to get that effect size. And if I was to use my handy dandy calculator, go into here, I'm just going to divide 288.203 divided by, that's between, sum of squares between, by the total, right? 2420.968, and it's going to be 0.11. So our effect size is 0.11. That's a small medium, or I mean a medium large, approaching large effect size. So we'll just call them medium large. And that's going to go right there. All right, so based on the p-value in our output, is the F ratio significant? Should we reject or retain the null hypothesis? And yeah, so we know this from previous classes that if you get a p-value that is less than 0.05, then it's statistically significant, and then 5.27 well exceeds what we saw here in the walkthrough. So here's kind of the model of significance values for F ratios, and it needs to be greater than 3.68 when you have alpha set at 0.05. I don't know if you can see that really clear. I'm going to have to zoom in a little bit. Yeah, that's a little bit, that's just right. So as you see right here, 3.68, if it's alpha level set at 5%, then that would be the threshold of statistical significance. And we do see that it met that threshold with an F value of 5.27. All right, so I think you can write that down and mention that P is equal to 0.007, and the F ratio is 5.27, which exceeds the cutoff that we see in the PowerPoint. It's probably a better way of saying that, but it gives you sort of an idea that this is the reason why we should reject the null hypothesis. Is there's certain estimations of the F ratio, and that has been met, and then the p-value is less than 0.05. And in this case, our exact p-value we have to give is 0.007. All right, and so now let's go ahead and move on to the next part, which is how much proportion of variance in the DV is explained by the IV, and is it meaningful? So what does that actually mean right there? So proportion of variance in the DV explained by the IV, and is it meaningful? Okay, so basically what this means is we have IV that is predicting or influencing the DV, So if I was to show you this scenario here where we have these three groups, and then we have one dV here. This is level 1, level 2, and level 3. But really what we have here is just one IV influencing one dV. So how much does this IV with these three levels, how much is explaining of this dV, which is weight loss? So when we have these groups and there are different levels to the diet plan, how much does that affect weight loss? And what we saw here when we did the multiplication, we got an eta square of 0.11. So that's how much influence that this IV has on this dV. There's approximately, you would say, right? There's approximately 89.89 that is left unexplained. This is unexplained. And maybe if we were to add an independent variable looking at their self-efficacy, maybe that could be another independent variable. That could be independent variable 2. And self-efficacy is also influencing this dV. And if we were to add this second IV, then maybe eta square would be 0.20 or 21. And then if we were to add a third IV, and perhaps that is something like how much sleep do they get, then that would affect their weight loss as well. So you have one group that gets 8 hours of sleep, another group that only gets 2, and then a third group that gets maybe 4 hours of sleep. And how does that affect their weight loss? And that maybe the effect size would be 0.35. And so the amount of influence that this IV has on the dV is 0.11. And based on the scale that we see here, 0.01 is a small effect size, 0.06 is a medium effect size, and 0.14 is a large effect size. So what we can say here is, based on the results, we have calculated an effect size that is approaching a large effect size, is actually a small medium effect size, small medium effect size, I should say. We have a medium, not small medium, but medium large effect size. Eta square. Just try to copy and paste that. Eta square equals 0.11.